Now, part two for chapter one is going to deal with the scientific method. Now, I know you've heard about the scientific method for years because my kids, when they come home, when they're in elementary school, talk about this. But let's see if we can approach it maybe just a little bit different. So, first off, we have this idea that we're going to try to solve some sort of a problem. So, we're going to use the scientific method. So that's just a process of explanation and also experimentation. So we can try to figure out what's going on and why it's going on the way that it does. Now, the first thing that you're going to do is you are going to make an observation. Now, what do you use to make an observation with? You use your five senses. All right, take just a minute. Can you remember your five senses? Let's see. Sight, hearing, smell, taste, and touch. Good job. I know you can do that. Now, we do have a little bit of a problem because our senses can be deceived and they're also not precise. So, the example that I use for that always is as I'm doing my little introduction at the beginning, I talk about how I went to a really small high school. There were 16 in my graduating class. Again, very small high school, and we were the large class. And I was the starting center on my basketball team. Now, I know it's really, really hard to see in this little bitty square um, much about me. But if I'm standing in front of you in the classroom, I'm like, okay, guys, how tall am I? And then I make everyone guess how tall I am. And we'll get a range of answers anywhere from about 5'9" down to about 5'2". Now, realistically, I'm right at 5'6". Okay, 5'5" and 7/8. But we talk about how our senses aren't necessarily precise, and that's why we use measuring instruments to be able to make sure that we have something that's really reproducible. Now, we also have a problem that our senses can be deceived. So let me see if I can deceive your senses. So again, let's see if I can deceive your senses. The first one, pretty simple. Which is longer, A or B? They're the same length. I know, but it appears that B is longer because your mind is playing tricks on you. Let's try some more. Now, on this one, are the horizontal lines, okay, do you remember what horizontal is? Remember that goes like you're laying down. Are the horizontal lines parallel, meaning that they're the same distance across, or do they slope, meaning one side is wider than the other side? What do you think? Oh, if you run your fingers down any two of them, you'll find that they're actually parallel to one another. Isn't that crazy? But because of the way they're slanted, it looks like they actually slope. Let's try some more. All right, so here's a few more kind of fun ones. On that first word, what do you read? Do you see good or do you see evil? On the second one, on that, no, let's do the bottom one first. So on that bottom right, what do you see? You might see a woman's face, or you might see Bill Clinton playing a saxophone. On the top, now this one's really cool. So the history of this one, it goes back to 1888, where a company called the Anchor Buggy Company had sent these out as postcards. It was this image, but it was um, I actually have a photo of it I use in some of my other classes. But it said, now you've seen my wife, what about my mother-in-law? So is this mother-in-law young and beautiful or an old hag? Which one do you see? Now, if you see the old hag, which generally is easier for me to see, there's her nose. She has a great big nose. And then she's got, I don't know, kind of a recessed mouth. There's her mouth right there. And she's got a big pointy chin. Now, if you see it as a young, beautiful woman, this person's looking over their shoulder. And so the nose actually becomes the chin of the young woman. That little wart up there is actually the young woman's nose. And um, the mouth and chin become the neck of the young woman. There we go. And that's her little choker. So if you need to, take a few minutes, look at it. But let's try another one of these optical illusions. Let's see if I can deceive your mind. Is this picture a picture or is it moving? Now, sometimes I'll have students that are like, oh my gosh, Miss Lumley, I can't look at it anymore. This is actually a still picture. Isn't that crazy? All right, two more. So this first one, it says, are these circles perfectly round or do they intersect? Yeah, your mind's going to play tricks. These are actually perfectly round circles. Oh man, my eyes are getting crossed right now just looking at that. So if you follow any one circle is perfectly round, they're not actually intersecting. Isn't that crazy? And then this, so I had to stop the video and I went back and I actually found the picture of the postcard because it was driving me crazy. So anyway, this is a picture of that original postcard that was sent out with it. If you see down here, you see my wife, but what about my mother-in-law? Find both on this side. And so that's kind of fun, just being able to look at that. So all right, so back to the scientific method. Again, you made some sort of an observation with one of your five senses. Just to note, we get most of our information, about 80% from sight. Hearing comes in second for most people. Of course, if you have a sense that is compromised in any way, the other senses tend to become stronger. Okay, so we're going to make our observation. Now, these observations can be qualitative or they can be quantitative. Qualitative means it's a non-numerical description. The sample is a liquid, it's cold outside, um, there's snow on the ground, the car goes fast. Quantitative means that we have a numerical measurement. So quantitative, instead of just saying the car goes fast, it really depends on where you're at as to what fast actually means. Because if you're in a school zone, then going over 30 miles an hour seems pretty excessive and you shouldn't be doing that because we want to keep the kids safe. If we're on the highway, well, going more than, we'll say, 80 miles an hour might be a little excessive. Now, I've done some work up at Kansas Speedway, and the cars on that track will go over 200 miles an hour. Isn't that just crazy to think of? Now, 200 miles an hour down a school zone is completely different as considered fast as to 200 miles on the racetrack, which really isn't that unusual. So when you have something that's quantitative, you have to have both the number, but you also have to have a unit. Here's another example. Um, let's say it's 20 degrees. How does that feel? You might think I put a unit on it, but I really didn't give you enough information. If it's 20 degrees Fahrenheit, it's pretty darn cold. If it's 20 degrees Celsius, then it's comfortable. It's room temperature. But if it was 20 Kelvin, oh my goodness, you are almost at absolute zero and you would probably not be alive to talk about it. So quantitative, you have to have the number and the unit. Now, once you've made your observation, we're going to formulate some sort of a hypothesis. We have some sort of a question that we're trying to answer. So this is going to be our possible reason why. This is our educated guess, our informed guess. So here we go. My observation is I go out in the morning and my car doesn't start. Why wouldn't my car not want to start? What's your first inclination? Battery is dead. So that's going to be my first hypothesis. My car won't start because it has a dead battery. And then I have to test it. So I look around, I see if I open the doors, it's the light come on, or is it super dim or not come on at all? Because if it doesn't come on at all, there we go. I'm tripping over my words. That means that the battery is dead. But if the light is really strong, then it's not the battery, it's something else. So then what I have to do is I have to revise the knowledge that I have, and I have to start all over again. Okay, my battery is dead. I have to formulate the hypothesis. My battery is dead because I'm out of gas. And then you keep going on and on after that. And it doesn't have to just be, how to start a car. These are things that you've dealt with in your everyday life, but you might not have thought about it as being an actual scientific method. If you watch much sports, my youngest is in basketball right now. The offense and the defense. Say you're on defense, and the offense comes down and you're playing a 3-2 defense and they score real easily. Okay, let's try a different defense next time they come down and see if that helps. Or let's change something about the defense to try to stop them more efficiently. So that is your performing experiments. Have to have testing, have to have experiments. Let's continue on. Now, those experiments that we do have to be really, really careful about that. So this one talks about um, just some things about those experiments. Experiments are going to be some sort of observation of natural phenomena. It does have to be carried out in a controlled manner. It has to be carried out in a manner that we can actually test. So whenever I was in college, we were working with, my background's textile chemistry. So we were working with, say, the strength of cotton. Well, the strength of cotton depends greatly on what the humidity is. It turns out cotton gets a little bit stronger if it's a little bit wet. So we actually had an entire room that was temperature and humidity controlled so we could be able to control the environment. The next thing is that results can be duplicated. So you want something that you can try again and again and again. That is really where we get into this scientific method. So if I was testing that cotton fabric, I'm testing the strength of it. I don't just do one test and then say, okay, I'm done. I test it multiple times. I would test it 10 times in the warp and 10 times in the weft for every sample of cotton that I had. There's a lot of duplication. And then finally, we want something that can be done by other researchers because we want to make sure that there's not something weird going on in our lab, that this is something that's going to be able to be shared and confirmed by other people. So um, if you can't duplicate it, then you have to question the results that you obtained originally. So a couple things to think about with that idea of experimentation. Now, once these experiments have been done time and time and time again, and you go back and you revise that initial hypothesis time and time and time again, when you finally get to something that withstands that test of time, that can be duplicated by a lot of different scientists and is generally accepted by all the scientists, we have a theory. Now, the observation is the law. Concise statement in words or equation about a fundamental relationship of nature. It can, so it can be in words or it could be in an equation like force equals mass times acceleration. We're not explaining why it happens. All we're saying is this is the observation that we've made. It summarizes what happens and we don't have any exceptions to this. Another example, the sun rises in the east. I mean, have you ever seen the sun rise in the west? Man, if you've ever seen the sun rise in the west, that was some party the night before. The sun always rises in the east. Now, the theory, the explanation why, remember that's the hypothesis that stood the test of time, that one can change. That one may change as we find out information. This one's the generally accepted hypothesis, but later on, maybe we find out there's a little more to it. So let's go back to that example. The sun rises in the east. Now on this one, this is a really obvious one where that theory has changed. Now, I hate to break it to you. You are not the center of the world. I know. I didn't mean to break your heart. Now, it used to be believed that the sun was the center of the universe. The sun, I said that one wrong. It used to be believed that the earth was the center of the universe and everything went around the earth. And so that's why the sun rose in the east, is because the sun was going around the earth. But today we know that's not the right thing. We know that Earth rotates, so that's why we get our day and our night, and it also revolves around the sun, and that's where our year and our seasons come from. But not only that, but the sun's not in the center of the universe either, and the sun actually moves, and the sun rotates, and the sun revolves, and that is discussed in a later chapter. But we found out new information. And so this generally accepted theory, which everyone kind of believed, did actually change. Now, a lot of times theories aren't going to change like that one, but that's a case in which it did. So that's a good place to stop really quick. Come back for the next part.